Welcome to e-learning in thermodynamics and fluid dynamics of our bachelor program in renewable energies and environmental technology. In this video, we will look at the Bernoulli equation, which is useful for a wide range of applications. For simplicity, we will assume steady-state incompressible flow. Steady-state means that all the system parameters are constant with time, and incompressible means that the density of the fluid remains constant. In order to derive Bernoulli's equation, we first need to understand what a stream tube is and then cover the principle of continuity. Bernoulli's equation is valid for fluid that is flowing through a stream tube. In a stream tube, fluid enters through the entry cross-section and exits through the exit cross-section, and no fluid can flow through the lateral surface. The principle of continuity states that mass is conserved within the borders of a given system, meaning that it can neither be created nor destroyed. In a steady-state stream tube, the mass flux M point is the same through all cross-sections. In cross-section 1, the mass flux M.1 is entering the stream tube, and in cross-section 2, the mass flux M.2 is exiting the stream tube. In the case considered here, the density ρ of the fluid is constant throughout the whole stream tube. In other words, continuity states that the volume flow rate V point is the same through all cross-sections. In cross-section 1, the volume rate V.1 is entering the stream tube, and in cross-section 2, the volume flow rate V.2 is exiting the stream tube. As the volume flow rate is equal to the product of the cross-section and the velocity of the fluid exiting the stream tube can be obtained by making use of the continuity principle if the cross-sections 1 and 2 as well as the entry velocity are known. Bernoulli's equation tells us that the sum of all forms of energy within a stream tube remains constant. It can neither be created nor destroyed. Therefore, the energy flux exiting the stream tube must be equal to the one entering it. But what type of energy is actually present in a stream tube? For now, we restrict ourselves to a frictionless case, in which no energy is added to or removed from the system via friction at the lateral surface of the stream tube. Therefore, only fluid entering the stream tube through cross-section 1 is adding energy to the system. Let us consider a cylinder of fluid in a pipe of mass m at cross-section 1 at a height h1 with respect to the ground. The potential energy of the cylinder equals the product of its mass m, the gravitational acceleration g, and the height h1. The fluid has a velocity v1 and thus a kinetic energy of 1/2 times m times v1 squared. Additionally, the manometer at point 1 is measuring a static pressure of P1. The work needed to press the fluid cylinder into the pipe at a pressure P1 is known as pressure volume work. In this example, the pressure volume work equals the product of the volume V of the fluid cylinder and the pressure P1. Since we are still neglecting friction, energy is only removed from the system by the fluid exiting the stream tube through cross-section 2. The fluid cylinder exiting the system, which due to continuity still has the same mass m, has an energy equal to the sum of its potential energy, its kinetic energy, and its pressure energy. As there are infinitely many such fluid cylinders of volume V moving through our stream tube, the equation can be divided by the volume V in order to obtain the pressure form of Bernoulli's equation. The unit of all these terms is Pascal. The three components of this equation are the gravitational pressure, derived from the potential energy, the dynamic pressure, derived from the kinetic energy, and the static pressure, derived from the pressure energy. Let us now apply the frictionless equation to a jet of water coming out of a tap. In this case, the entire jet can be considered as a stream tube. The gravitational pressure decreases as the water loses height throughout the fall. The potential energy is converted into kinetic energy, which means that the velocity and thus the dynamic pressure is increasing and the potential energy reducing. Next, we consider the flow of water through a pipe with varying cross-sections. In cross-sections 1 to 5, we are measuring the static pressure using water columns. Between any two of those points, a stream tube can be created for which Bernoulli's equation is valid. Neglecting friction again, the sum of gravitational pressure, dynamic pressure, and static pressure remains constant along the stream tube. In this case, the stream tube runs horizontally, which means that the gravitational pressure is constant and therefore cancels out in the equation. The sum of the kinetic pressure and static pressure is therefore constant. As the pipe narrows, the velocity increases due to continuity. Bernoulli's equation then tells us that the static pressure must decrease as the pipe narrows, which we can see from the lower water columns at cross-sections 3 and 4. As the pipe widens again, the inverse happens and the water column at cross-section 5 is at the same height as at cross-section 1. However, in real pipes, there is a pressure loss due to the friction between the fluid and the pipe. This loss is proportional to the dynamic pressure, and thus to the velocity squared. Furthermore, it depends on the friction factor lambda as well as the length L and the diameter d of the pipe. Between cross-section 1 and cross-section 2, there is already a small loss due to friction. Between cross-section 3 and cross-section 4, the fluid has a higher velocity, and therefore the pressure loss due to friction is higher over the same distance. But where in Bernoulli's equation should we insert the pressure loss term? The steady-state Bernoulli equation tells us that the energy flux entering the system is equal to the one exiting it. Friction removes energy from the system and therefore belongs to the terms of energy exiting the system. In the following example, a family is filling their pool with water from a lower-lying lake. The water is drawn into the pipe at a level H1 with respect to the water level of a lake and pumped to a level H2. The stream tube extends from the water surface of the lake through the pipe and the pump all the way up to the water surface of the pool. As the surfaces of both the lake and the pool are very large compared to the cross-section of the pipe, the velocities v1 at the entry of the stream tube and v2 at the exit on the pool surface are negligibly small due to continuity. Both dynamic pressures can therefore be neglected. The static pressures on the water surface of the lake and of the pool are equal to atmospheric pressure and are therefore equal. These terms therefore cancel out of the equation. Only the gravitational pressures ρ times g times h1 and ρ times g times h2 remain. However, there are two more terms which have to be added to the equation. The pump is adding energy to the water by increasing the pressure in order to overcome the elevation difference. This pressure increase, delta P pump, is included on the left-hand side of Bernoulli's equation with the terms adding energy to the system. Friction removes energy from the system and therefore decreases the pressure. This pressure loss delta P friction is therefore included on the right-hand side of the equation with the terms removing energy from the system. Bernoulli's equation in the case of incompressible fluids can be applied to gases. Gases are compressible fluids in general, but there are situations in which the density of a gas does not change, for example in the case of a pitot tube, a device used to measure velocities. In this example, we want to measure the velocity of a zeppelin. We apply Bernoulli's equation between point 1 and point 2. The sum of gravitational pressure, dynamic pressure and static pressure is the same at both points. The 2 points are almost on the same elevation level and the density of air is relatively low. Therefore, we assume the gravitational pressure at point 1 to be the same as at point 2, and therefore those terms cancel out. At point 1, the approaching air fills up the pipe and stagnation occurs. The velocity at point 1 is therefore equal to 0, and the dynamic pressure can be cancelled out as well. The pitot tube has to have an aerodynamic shape so that the velocity at point 2 matches the velocity we want to measure. If we then know the static pressures P1 and P2, which we can obtain from the 2 manometers inside the pitot tube, only the velocity at point 2 remains unknown and can be calculated. In this video, we have introduced the steady-state case of Bernoulli's equation for incompressible fluids. We have shown that Bernoulli's equation represents an energy conservation and can be applied in many different situations.